Hey y'all, how you doing? Hope you're having a good day. So today I'm going to continue discussion on quantum nonlinear optics, and we're going to solve for the second and third order perturbed probability amplitudes using time-dependent perturbation theory. So in the last video we arrived at some equations. So this equation was the first one where we made our approximation, and it says that the probability amplitude of being in state y up to nth order perturbation is equal to a constant times the sum over all the states z, and we're integrating from negative infinity to time t. And on the right side here we have the probability of amplitude of being in state z, and it's the n minus 1 perturbed part. And we got a phase factor here, and we have a first order perturbed Hamiltonian here. And in the last video we assumed the perturbation was oscillatory, so we could write this v part as some spatially constant part plus some oscillation part, which we just wrote as an exponential, and we summed over all the frequencies I. So that's where this I comes from. And yeah, in the last video I didn't have this exact equation, but I had pretty much the same thing. I just relabeled. Here I relabeled the subscripts. And essentially we used this formula, except plugged in A for Y and also plugged in G for Z, but we also assumed that we are absolutely positive that we know our system is in state G at time t equals negative infinity. And that's how we got to this. And negative infinity is nicer to work with because when you do the integral you don't get a 1, whereas if this time is 0 then you get a 1 instead of a 0, which makes things easier, but there is the approximation that you have to wait a long time before perturbing the system. Okay, so I hope that all makes sense. And now we're going to use this equation to solve for the second order coefficient. And I'm going to rename y, I'm going to call it b. And, okay, yeah, so n is 2. Oh, sorry, another thing. In the last video I forgot a negative sign, which I put that here. But it doesn't matter too much because a lot of the time this v is going to have a negative in it, which is going to cancel this. Okay, anyways, okay, I already said the y is going to be b. The z is going to be a. And the n minus 1 is going to be 1. And, okay, this might trip some people up. It tripped me up. But we're going to have a second order perturbation. It's going to be a different perturbation, which sort of means it could be like a second light pulse. And that light pulse could be different than the first light pulse, and it might be made up of different frequency components. So we're going to have to sum over different frequencies, and I am going to use the index j for those frequencies. Okay, so this is the expression for our second order perturbed coefficient. Okay, all I did there was plug this in for here, changed all the t's up here to t primes. When I first wrote this, there shouldn't be the prime there. I plugged in the oscillatory perturbation, summing all the frequencies j, and there's that part. Now I'm going to pull out all the constants that don't depend on t prime outside the integral, and I'm going to perform the integral. Okay, now here I want to say something because I'm going to rewrite this exponential part. So the way I define the omegas, so omega AG is equal to omega A minus omega G. So omega AG plus omega BA is omega A minus omega G plus omega B minus omega A. Omega A's cancel. You get omega B minus omega G. Gonna call that omega BG. Okay, so that's our answer for the second order perturbed coefficient. We can simplify a little bit more by canceling the i's, get rid of the negative, and I'm going to rewrite it on the next page and try to make it look clean so you can read it. And then we're going to do the third order coefficient. Okay, now I wrote that a little bit cleaner. Now I am using this equation here again, but this time n is 3. I'm going to put c in for y, and I hope that's not confusing because it's going to be c sub c. For n minus 1, it's going to be 2. Z is going to be b. And yeah, I think you'll understand the rest. Okay, so there we go. There's our third order perturbed coefficient. And just to remind you what all the indices and things mean. Okay, so G is the ground state, and we assumed that we're 100% sure our system started there. And A, B, and C are just higher lying states than state G. And this sum is for the states. And so the sum here is the same thing as summing over A and then just summing over B. Or you could reverse them. And the IJK is all the frequencies. So we could have 3 different perturbations come in at different times. And they could be, for example, laser pulses that is made up of different frequencies. And here the V, the first one here, V AG I naught, just means it's a time-independent quantity here. And usually, at least most likely in the future, and most likely if you're watching this video even, V is going to be equal to negative mu dotted with the electric field. So this would be rewritten as, so for instance, VAG would be mu AG times the electric field that went with that part, I. Except that it doesn't depend on time there. The time dependence for it is in here. Okay. And that's also where the minus sign shows up, so that's why minus signs out here I'm not being too picky about. Yeah, just thought I should let you know that. And okay, that's it. We did it. And okay, thanks for watching. In the next videos, we'll be using these results to get the polarization and susceptibilities. Okay, thanks for watching, and have a great day.